right, let's begin lesson 2 for our vectors. Yesterday we learned about magnitude of a vector, which remember is the length of the vector. Today we're going to talk about component form, algebraic vectors, position vectors, and all that good stuff. Now, an algebraic vector is another way to represent vectors so that we can find magnitude and direction. Algebraic vector is going to be written in what we call component form. Component form looks like this. Okay, you're going to have the name of your vector equal to two values from the vector, and they're surrounded by a less than and a greater than sign. It looks like an ordered pair without the parentheses. It has a less than and a greater than sign. So again, this is component form. Okay, so this is the way that we write our algebraic vectors. Okay, so we're going to talk about a specific type of vector right now, which is a vector that's in standard position. Okay, a vector in standard position has its initial point on the origin, and then it's going to extend to some point in the coordinate plane where your terminal point will be. This is what it looks like. Okay, here's your x and your y axis. Your initial point is right here at the origin, and then it's extending to your terminal point. Your terminal point in this case is AB. Now, if you're going to find the magnitude of this vector or the length of this vector, remember you always do x2 minus x1. So that would be A minus 0, which is A. And then you do y2 minus y1, which is b minus 0, which is b. So if that's the case, then in order to find the magnitude, we can adjust the formula, okay? So we'll get to that in just a moment. All right, so if a vector is in standard position, now if it's in standard position where the initial point is at the origin and then it extends out into the coordinate plane, it's called a position vector. So make sure that you make note of that. In your textbook in section 9.4, it doesn't talk about standard position, it talks about your vector being a position vector. So know that standard position and position vector both mean a vector with the origin as its initial point, okay? If a vector v is in standard position with the terminal point at AB, then the component form for the vector is vector equals less than, then the AB, and then the greater than. Again, this is component form. Component form is how we write our algebraic vectors. In order to find the magnitude, which is the length of the vector, like I just told you, if you do A minus 0, you get A. B minus 0 equals B. So we can adjust our formula, and instead of doing x2 minus x1, and then squaring it, we can just take whatever A is and square it. Instead of doing y2 minus y1 and squaring it, we can just take b in our vector and square it. Add them together and take the square root. So it's an adjusted formula to account for the fact that we're doing a minus 0 and b minus 0. Now, the direction angle is the angle that's formed from the positive x-axis up to the vector itself. So this right here is my direction angle theta. In order to find your direction angle theta, the only thing that you have to do is take b from your component form and put it over a from your component form, and you'll have to do your inverse tangent to actually get the angle. So tangent of theta, which is going to be your direction angle, is b over a. Then you're going to do the inverse in order to actually find out what theta is, which is your direction angle. All right, now here's a few notes that I wrote on the side to kind of help you out. All right, when a vector is written in component form, remember it's an algebraic vector. The initial point is the origin. The terminal point is some point P. We're representing it with the ordered pair AB. So that when you put it into component form, you're just taking the point of your terminal side and putting it into the component form. Now, it's called standard position or a position vector. Algebraic vectors represent what we call driving directions to get from your initial point to your terminal point. So if you have a vector that's in standard position, 5 and 4, okay? Remember, you're starting at the origin for your initial point. And then you're going to go 5 units to the right, and then you're going to go 4 units up. And that will get you to your terminal. Initial to terminal. So this is going to be your right and left. This is going to be your up and down. Of course, depending upon if it's positive or negative. Okay? So, again, algebraic vectors represent driving directions that will get you from the initial point at the origin to the terminal point. Okay, so this would be our coordinate plane. This would be the origin. I would go 5 to the right and then 4 up to get to my terminal point. Okay, all right, so with all of that information, and that was a lot of information in just 5 minutes, let's take a vector that's written in component form, okay, and we are going to find the magnitude and the direction angle. Since we know that this is in standard position, we know that it starts at the origin and it's going to end at 7 and 24. All right, so instead of doing, when we find the magnitude, instead of doing 7 minus 0 and 24 minus 0, we're just wasting time doing that because of the zeros. We can just take A, which is 7, and square it. And then we can take B, which is 24, and square it. Okay, and add those two together and take the square root. All right, so we know that 7 squared is equal to 49, and we know that 24 squared is equal to 576. Okay, let's add these two together. We're going to get 625. All right, now the square root of 625 is just 25, because 25 times 25 is 625. So the magnitude, or the length, of this vector is 25. Now let's look at the direction angle. That's going to be from the positive x-axis up to the terminal side of the angle, which is your actual vector. So we're looking for theta. So the tangent of theta is equal to b over a. B in this case is 24 over A, which is 7. That's what the tangent is. We want to find the angle itself. So to find the angle, we're going to have to find the inverse of our tangent. Okay, so let's go over here and let's do second tan to find the inverse and put 24 over 7. All right, so 7... let's go at 2 decimal places, 73.74. So theta is 73 and 74 hundredths degrees.